and let's get this party started. So where were we at when we left off yesterday? So Tuesday. So Tuesday, we sort of sketched the derivation of the arc length formula. And so to remind you what that was, the length of a curve from A to B the length of a given curve on an interval AB is the integral from A to B, 1 plus, you take the derivative and you square it, add 1 to it, and then take the square root. So it's a cumbersome formula. It's not hard to memorize, but it is a scary looking thing. And the key observation is to note the radical makes evaluating these types of integrals very difficult. So we saw that yesterday. In particular, we saw that when we tried to evaluate or determine L. Or in particular, the length of y equals the square root of x on 0, 1. So we ran into some problems. And the reason, you might say, why did you choose that example then? Why didn't you choose one that we can do? Well, that's the point. Sometimes you need to realize that not everything is doable, particularly the way we would hope. So we're going to get to that in a second, and we're going to show you how to do these homework problems. So just to give you full, what do you want to say? To be complete, we'll remind you what that integral looks like. So let's recall y prime here is 1 over 2 root x, and that implies that y prime squared is 1 over 4x. And then what that means is that this integral from 0 to 1 is this. So it turns out we are able to sort of do this particular integral. However, it is not an easy one. And there's another couple nuances here you might say. You might say, okay, you might graph the square root. You might graph the square root function, and you might say, okay, great. This is what the curve looks like. It looks like this on 0, 1. I can just, oh my God, I hate when this marker loses it. So the square root function looks like this. I'm trying to just sketch it. So this is the 0.11. And a couple things to notice is, in particular, is we want to know the length of this green line here. But notice that 0 is not even in the domain of this integral. So that's another subtlety. However, the picture suggests that there has to be some length to this curve. And so what you're noticing right away is there are challenges here. Does anybody have a question before we sort of move on to what we can do and maybe how we can make sense of this particular problem? So, couple issues. The square root evaluated at 1 plus 1 over 4x. This is undefined at x equals 0. That's one issue. And the other issue is, so we'll call this 1. And then the second issue is there's no obvious antiderivative. Now, of course, if you go to some fancy software, they're going to tell you what it is, but it's not at all obvious how you might get that. So again, let me repeat this. We look at that green curve, or if you go to Desmos and graph this, you're going to say, okay, that curve has to have a length. But then we say, okay, and we believe the length is given by this integral, but right away we say, okay, there's two issues with us trying to evaluate this integral. So what is the moral of this particular problem? The moral is we need to learn more stuff. That's the moral. So okay, so if we say that, we're going to do that. But before we do that, let's just do one or two basic examples of arc length that you can do. Now, if you look about what the issue here was with the previous problem is that square root shows up. The square root in every case, in most things we're doing, not just in calculus, but the square root often poses a problem. It doesn't have nice properties, like you can't break it up over addition. It's hard to work with. That doesn't mean we can't work with it. That just means we have to be sort of more careful. So let's look at an example where the square root doesn't become an issue. So here's one we can do. So let's compute the length of y equals x to the 3/2 on 0, 1. So you might say, okay, why not x squared or something that's more familiar? Well, it turns out x squared is really difficult too. That's a famous problem. It took a long time for humans to figure it out. This one we will be able to do. So here's the solution to this guy. So the first thing you need to notice is that y equals x to the 3/2. And that tells us right away that the derivative is 3/2 x to the -1/2. And the beauty of using the 3/2 is now when I square it, the power goes away. Excuse me, it's not -1/2, it's +1/2. 3/2 minus 1/2. Excuse me, 3/2 minus 1, geez, is 1/2. So this becomes 1/2. And then when I square the derivative, I get 9 force x. And so this means that the length becomes integral 0 to 1 of 1 plus 9 force x. And unlike the example we started on Tuesday, the variable here is in the numerator. It's not in the denominator. So this is going to be a very simple u substitution. So let's do that. I'll do it on the next page so it's we can have lots of room. Does anybody want to say anything before we do that? Comments, questions? No? So again, I strategically chose the power of 3/2 here because I knew once I took the derivative and squared it, then the power would go away. And that makes this problem, in many ways simple. Now, I'm not suggesting that it's simple to you, but I mean, relatively speaking, if we were considering all the integrals out in this planet, this is a relatively simple integral. We just have to do it properly. So we're going to set y equal to 1 plus 9 force x. And that tells us that y prime, or let me write it as dy dx, be more consistent. Dy dx equals 9 fourths. And then if x is 0, then y is equal to 1. And then if x is 1, then y equals 13 fourths. So what I'm doing there is I'm getting my new bounds in terms of y. So we've talked about this numerous times. I like to change my bounds. I believe, Zafalgar, you were the first one to mention you didn't want to do it that way. That's fine. You can do it however you want, but this is how I'm doing it. I mean, you can't do it however you want. You have to do it with a legal way. Your method is completely legal, though. And so what we have then is we have the length which started like this, turns into the integral from 1 to 13 over 4, square root of y. And then what is our dx? Well, our dx, if we sub it in, is 4/9 dy. So to integrate the square root of y, we note that square root is the same thing as power 1/2. So you add 1 to 1/2, you get a new power of 3/2. You divide by 3/2, that's the same as multiplying by 2/3. So what you get is you get 4/9 times 2/3 y to the 3/2, evaluated from 1 to 13 fourths. Which becomes 8 over 27 times 13 fourths raised to the 3/2 minus 1. And there's not much more you can do. If you wanted to, you can maybe simplify that 13 fourths thing a little bit, but we'll just leave it as is. Does anybody have a comment or a question about this? Did I make a mistake? Going once. Going twice. Supposed to count to 10 seconds. Anytime someone has a question. By the way, I mean, at this point in your life, it's, you know, I know you guys sort of hate arithmetic. So how did you get 4/9 in front? Okay, so look at this expression right here. When I solve that for dx, I get 4/9 dy is equal to dx. So that's why the 4/9 dy, so if I change my color here, maybe make it, if basically I'm, you know, what this change of variables theorem kind of says is it says we can pretend dy dx is a fraction and we can cross multiply. So you get, if I take 9/4 to the other side, it becomes 4/9, and then we get dy is equal to dx. Does that make sense? Does that clarify for you? Was it you back on it? I missed who. Oh, why the chat doesn't. Yep, very good. By the way, you know, it's not hard to simplify. I should actually do it because, you know, one of the things that you guys should be able to do is simple numerical things. I mean, look, 4 to the 3/2 is not hard to do in your head. That's the number 8. 4 to the 3/2 is the same thing as 2 to the 3rds, which is 8. And what's 13 to the 3/2? Well, that's the same thing as what? It's just 13√13. So if you want to write this clean, you can, and you should verify this for yourself without a calculator, that you get 1/27, and then it's 13 square roots of 13 minus 1. You should verify that for yourself. By the way, it's worth pointing out, and if you wonder why, I'm not some magic magician, I'm not some like genius, I'm not some weirdo who does arithmetic in their head very wildly, but in general, if you have any number a raised to the 3/2, how are we reasoning this? Well, one way to think about this is rewrite 3/2. 3/2 is the same thing as 1 plus 1/2, is it not? So this is a raised to the 1 plus 1/2, which you learn is the same thing as a to the 1 times a to the 1/2, which is a square roots of a. So that trick works with any number a, provided you can take its square root. And so for 13, you get 13√13. If it's 4, you get 4√4, which is 4 times 2, which is 8. And that's why the 8's disappear. So that's thankful to the good old middle school teachers at Francis McClure Middle School back in the early 1990s. And they taught me that, and I listened because my parents bribed me, and if I did well in school, I got to get stuff. That's how they did it, which is weird. In other cultures, they beat the hell out of you unless, you know, everything I heard about, I mean, I shouldn't speak on other cultures if I don't know them, but you've heard rumors like in certain cultures, like if you don't do well in school, it's an insult to your family name, right? For some strange reason here in the United States, it's cool to suck at math. I never understood that. But my dad knew better. He said, I will bribe you. The more good grades you get, the more shoes you get, the more Jordans you get. And I said, I like it, Dad. I like it a lot. And I will now bribe my children with toys and Barbie dolls, and it works. Teaches you work for what you want. Anyhow, shouts to Mr. Bell and the 6th grade teachers at Francis McClure. I remember all my teachers. He used to always have. All right, that was fun. Okay, mask on. Any questions about this? Now, this is one of the rare ones that is simple. So this is a, let me say this. That's the bad news here. So the above integral is one of the rare line integral, not line integrals, that's getting ahead of myself. Not line integrals. One of the rare arc length integrals. That is quote unquote easy. And I don't say easy in a disrespectful way. I don't mean easy to you necessarily. I mean easy in the world. Most are very difficult and or impossible to do exactly. So most are very difficult or even impossible to compute exactly. So on the homework, if you look at the homework, I gave you 3 of them to do exactly. I gave you one similar to what we just did, which is straightforward. Then I gave you 2 ones that are a little more challenging because they're going to require some fancy algebra. So let's do one of them. Let's do the one you brought to me just so we can show you. So let me write this down because this is helpful for your brains. On the homework, what is it? Homework 9. So, or excuse me, number 9. So on homework number 2, 9 is similar to the last example. (10) and 11 are challenging. So we'll do one of them. I'll do 11. Or no, not, am I losing my mind? Yeah, no, 10. No, which one did you bring me? You brought me 10, so I'll do 10. Shobit, you wanted to do 10, or you asked about it at least, so we'll do it. And by the way, 11 is very similar to 10 in how you do it. It relies on some algebra that most of you forgot, just like I did. I forgot algebra 2 at one point, only I don't forget it anymore because I use it all the time. I don't care if you learned Spanish as a kid, or if you were born in Lisbon and you spoke Spanish until you were 10. If you spent 15, 20 years never using it, you're going to forget it. Heck, even if you spend maybe 6 months never using it, you might forget it. And that's what happens with us with math. Even if we learn it, we often forget it. But that's okay. That's why we're here to remind you. At least I empathize with you. I get it. Okay, let's do it then. So the function, and by the way, this is not some phony problem here. This is, you know, I mean, it's a simplified version of a real world problem. You might say, who's building a road using this? Well, okay, go read the engineering and how we theoretically devised the most efficient roads, whether it's highways. Think they just lay concrete and let you drive on it? No, there's a science to it, right? Now, they probably don't measure out how much paint they're going to use. They'll just charge that to the tax gain, but let's pretend. All right, so here's the function we have in number 10. It's a scary looking creature. So we have the function y equals log x minus 1/8 times x squared. And what that tells us then is that tells us that the derivative y prime is 1 over x minus 1/4 x. Now, at this point, you don't have to do anything. You could just square it. I don't want to square it. I want to make it a little cleaner. This is just my preference. If you want to square it right now, that's fine. What I like to do is I want to write it as one term. So in order to do that, I need a common denominator. So what this becomes is this becomes 4 minus x squared all over 4x. That's just how I chose to do it. Now, why did I want to do that way? Well, now when I square it, I can square upstairs a little cleaner. So this is 4 minus x squared quantity squared over 16x squared. Okay, now what I'd like to do is multiply out the numerator. That is a perfect square. Foreshadowing. The numerator is a perfect square. It's something squared. By definition, that's a perfect square. And if we multiply it out, we get 16 minus 8x squared plus x to the 4th all over 16x squared. So let me repeat, and this is very, very, very important. You learned all about this in algebra, and you absolutely, positively, almost undoubtedly forgot. This numerator is a perfect square. So that's a very, very important thing. You should keep that in mind when you're doing problem 10. You should keep that in mind when doing problem 11. Now let me digress for a second to explain why. Knowing what we know about square roots, no, it will not matter because you're going to get the same thing. Now, wait a second. You said 4 minus x. I'm confused. Could you do x minus 4? Okay, yeah, you could, but you have to be careful with that. So the question was asked, can it be x squared minus 4? And the answer is here, yes, but it would be incorrect to write it. That's because you would have gotten that. Let me say it this way. That's a good question, but let me say it as carefully as I can. So it's true that negative x quantity squared is equal to a squared. So that's true from no matter what a is, which means that means that 4 minus x squared quantity squared is the same thing as x squared minus 4 quantity squared. That's true, but you're now reversing that logic. It's not necessarily true if you go the other way. What I mean by that is just because we're told that some number squared is, say, 9, you don't know if it's -3 or +3. Does that make sense? So let me repeat that again. It's if you take two numbers, one positive and negative, and square them, you get the same thing. But it's not necessarily the case if you undo that. So you have to be very careful. So what you said is it comes with a technicality. It is true that these two things are equal, but it's clearly not true that 4 minus x squared is always equal to x squared minus 4. So you have to be very careful how you reason that. Does that make sense, hopefully? Well, how did you get x minus 4, though? I'm not quite sure where you're even getting x minus 4, Emily. I mean, if you combine this, if you find the common denominator, the minus sign is here. So when you find a common denominator, it wouldn't be x squared minus 4, it'd be 4 minus x squared. Does that make, okay, good. Very good. Now, but that's actually an important question because, if we're not careful with that, we could mess up what's happening later. For years, that was always like the most commonly missed question on like standardized tests like the SAT. They would ask you to solve, they would say, okay, let's solve x squared equals 9. And of course, all you guys do is you just rat off 3. But you fail to forget that -3 is also a solution. And then you flunk. And then you don't get the scholarship, or you don't get the whatever they do. Put you in a category. Okay, so let's go back to what I was saying about the numerator. The key observation is the numerator is a perfect square. So when it's a perfect square, that means we can easily go from this line right here that I'm circling over down to this line, and we should be able, theoretically, be able to reverse it. So one of the things that most students are good at is most of us can handle multiplying out, going from this to this. Most of us are good going from this line to this line. What most of us, myself included years ago, and you guys for sure now, what you guys can't handle well and what you guys stink at is reversing it, starting with this and recognizing this. So all those algebraic homeworks that they wanted you to do when you're in school and you said, this is stupid, when will I ever use it? Well, here's a time. So recognizing how these two things are the same is very important. Okay, so let's continue. So the integral now, the length we're after is the integral from 1 to 2 of this ugly square root. So it's 1 plus. Now on the previous page, we calculated it. So we know what it is. It's 16 minus 8x squared plus x to the 4th. So this is 16 minus 8x squared plus x to the 4th all over 16x squared. So this is what we have to integrate. And right now it looks like an absolute atrocity. But fortunately, some very useful algebra is going to save the day. So what I was saying earlier is that when you have a square root in an integral, it poses a problem. We saw that. We saw at the end of class Tuesday. It didn't pose a problem in the previous thing because it was a simple substitution. But you can imagine that in general it's going to be a problem. And the only way to just abolish a square root, the only way for it to disappear, is if what's inside is actually a square. And it's going to turn out that this ugly thing, 1 plus blah, is actually a square. It's a perfect square. We just have to figure out how and why. So the first thing I'm going to do is I'm going to combine this thing. So this becomes 16x squared, and then it's plus 16 minus 8x squared still, plus x to the 4th. And then this is all over 16x squared dx. Now the beautiful thing, look at this big fraction. The denominator is a perfect square already. We know it's square root, it's 4x. The numerator though, that ain't. At least as we have it written, it's not obvious. So what I'm going to do is I'm going to combine my like terms. And 16x squared minus x squared, or 8x squared, this being, when I add them together, becomes plus 8x squared plus x to the 4th. And the key observation, which every algebra student in the world knows, actually not in the world, maybe in every country but here, is that the numerator is now a perfect square. So all I did from the middle step to the bottom step is I took my x squared terms and combined them. I'm allowed to do that. If I have 16 apples and I give you 8 apples, I am left with 8 apples. 16 minus 8 is 8. And so here's where the magic happens, is they say the numerator is nothing more than 4 plus x squared quantity squared. So that perfect square, and you can multiply this out and verify it for yourself. But what I'm using here is the numerator right here. So this creature the star term, and this same little recognition or this same observation is going to help you when you do problem 11 as well. And by the way, you can verify this for yourself. Don't just trust me. If I come here and I say, okay, 4 plus x squared, quantity squared, if I multiply this out, I get 16 plus 4x squared plus 4x squared plus x to the 4th, which is exactly what I have here. And so why this is sort of magical in a way, but it's not really magical, it's pretty reasonable, is the numerator and the denominator are both perfect squares. So they're going to cancel out the square root. So all this time, we just had to figure out the appropriate algebra. So really, the difficulty in this problem is not the calculus. Turns out the difficulty in this problem is the algebra. Okay, so let's go to the next page, and what happens? The square root kills the squares. So what we're left with is, oh, I don't want to use that. I'll put a black marker back. What we're left with is the following. Thus, L is simplified to integral 1 to 2. Upstairs is just 4 plus x squared. Downstairs is 4x squared, excuse me, 4x. So we'll go back to the previous page just to make sure you see that. So the numerator was quantity 4 plus x squared squared. When the square root hits that, the square and the square root cancel. And then the denominator was 16x squared. When the square root hits that, it's 4x. So just to refresh yourself here, the square root is going to kill the squares. Well, now we have a very easy integral, and it's, if you recognize that, you can break it back into two pieces. This becomes 4 over 4x plus x squared over 4x dx, which is the integral from 1 to 2 of 1 over x plus 1/4 x dx. And so you get log x plus 1/8 x squared evaluated from 1 to 2. So it's log of 2 plus 1/2 minus log of 1 plus 1/8. And at the end of the day, log 2 survives. 1/8, when you take it away from 1/2, is the same thing as 4/8 minus 1/8. So 1/2 is the same thing as 4/8. When I take away 1/8, I get 3/8. So I get log 2 plus 3/8. Provided we didn't make an error. And by the way, don't forget that log of 1 is equal to 0. So this is a very sort of, I don't want to say challenging, because once you see the trick, it's not hard, provided you understand the algebra. But this is a problem that unless someone shows you this trick, you're likely not to remember it. And that's okay. That's why we have class, right? Does anybody have a question about this? Going once, going twice. Again, it's not, keep hitting the wrong button. Oh yeah. There it is. That's the excitement I like to hear. Okay, so there you go. That is a challenging problem. I hope you go through it though and make sure you can do it. You'll feel good about yourself. Okay, so let's move on. So a very similar derivation gives us information about surface area. So the next thing we just want to, and I'm not going to go through the derivation. I'll give you the formula and we'll show you how to, but very much of the stuff we just said about arc length is going to apply to surface area. So we can also derive a formula for the surface area of a surface generated by rotating a curve. So the good way to think about this is imagine you generate your solid like we did before, and just think of its surface. How would its surface be generated? Well, its surface would be generated just by rotating the curve, not the whole region. So, for example, let's just draw a quick little sketch here. If I took some function, say I'm just looking at this piece. Say it's y equals f of x. And so if I rotate it, if I rotate this curve, don't worry about, I mean, you could rotate the region, but if you just rotate the curve, if you rotate the curve, what we end up getting is we're going to get some surface. It's sort of going to look like a horn, right? So I would encourage you to sort of think of this surface as a horn. So I'll write it like that. So first off, this is hollow. So think of this as like a lampshade. Or a horn, you know. And I'm thinking of a horn in like the musical instrument type thing. Does anybody have a question about this? Now, much like with the volumes before, I mean, you can even solve many of these problems without drawing a picture, but I highly encourage you try to use your imagination to make sense of this. Okay, so what is the arc or the surface area? So the surface area so one can show the surface area is the integral from A to B, and the formula is very, very similar, as you would imagine, to the arc length. It's 2 pi f of x. You could think of that as the circumference, and then you have to multiply it by the arc length. So let's do one like on your homework. So let's rotate, say y equals the square root of x. About the x-axis on 1, or let's say 0, 1, to obtain, I guess let's just say 1, 2. We'll do 1, 2. To obtain a surface. Determine its area. So we have to plug this stuff into the formula. So the solution here. So we need to do y prime squared. So y prime is 1 over 2 root x, which we saw already. And y prime squared, just like we saw last class, is 1 over 4x. So what's the area? The area is the integral from 1 to 2. We have 2 pi f of x, which is the square root. And then you have 1 plus 1 over 4x dx, which looks bad. But this one turns out to be even easier once we make the appropriate algebraic move. So what happens is a lot of times students will get here and you get stuck. Does anybody, I mean, if you think about this, the observation here is to remember a basic fact you likely learned in 8th or 9th grade about radicals. You can multiply radicals. You can't add or subtract them if they're different, but you can multiply them no matter what. So I'm going to pull the 2 pi out. And then when I combine these two radicals, I get 1. And so I'm left with x times 1 plus 1 over 4x. And when I multiply, or when I distribute, I'm left with x plus 1/4. Now, we have integrated these creatures many times. So for the sake of argument, or I shouldn't say for the sake of argument, in honor of saving some time, the way you're going to do this is you're going to, I'll spare you the details. You're going to say, you should do it for yourself. You're going to set y equal to x plus 1/4, and then your dy sort of dx is 1. And then you do all your simple, you change your bounds and do all that fun stuff. And what you're left with is it'll be 2 pi, and then it's going to be what, 9/4 minus 5√5 over 12. So you can fill in the details. It's not terribly difficult. Does anybody have a question? Okay, so hopefully you'll fill in the details there for practice. But this, again, this turns out to be a very rare surface integral that is quote unquote easy. All right, so let's make sure we beat that fact into your head even more. So just like arc length integrals, surface area ones are typically challenging. So one idea we can use is to use Riemann sums to approximate the integral. So don't forget, all of these integral formulas were built on the fact that we chopped something up, examined sort of the small piece, understood the geometry of the small piece, and then said, let's add them up. And when we took a limit, we got an integral. But what that means then is with Riemann sums is the following. So in general, an integral of some function, f of x dx, is approximately the value of a Riemann sum. And the approximation theoretically gets better as n increases. But this is one strategy. Yeah, and so we're not using series yet. That comes later. Right now we're just worried about, this is just a Riemann sum. So remember, this sigma means we're going to add up n things. So the questions of Volker asked if we're getting this topic called series, and we will, but series comes in a few weeks. We're not there yet. So if you go back to Calc 1, we did this. Before we even talked about the integral, we asked you to approximate areas using Riemann sums. And so what we're telling you now is we can do the same thing on these arc lengths. We can do it with surface areas, volumes even if we wanted to. So Again, let me emphasize the integrals that arise in arc length and surface area, and not just them, but any integral. If it's very challenging to do exactly, one option is to approximate it using a Riemann sum. Particularly if you have software. If you have a computer and if you can write simple computer code, you can have a computer approximate it for 1,000 or 10,000 terms. But let's do one. On the homework, I'm asking you to do this by hand. And if you look at problems, if you look at problem 13 and 14, this is what we're asking you to do. So we'll show you how to do, we'll do 13, and then you guys can do 14 on your own. And then we'll call it a day. And then the only thing left that we didn't talk about yet is problem 15, but that'll be the video I give you tomorrow, so you can learn that. It's a great problem in physics. Okay, so let's do an example. So let's illustrate this idea. So here we have y equals x squared on 0, 1. So let's write this down. The length of y equals x squared on 0, 1. So part A says, what is the integral? Do not try to integrate it. And the reason I'm saying do not try, I mean, you could if you wanted, but we don't know how to do it yet. It requires some fancy maneuvering we didn't talk about yet. So let's just note that. So y prime is 2x and y prime squared is 4x squared. Thus, the length is this integral, 0, 1, square root of 1 plus 4x squared. So here's the first thing I want you to say, or I want you to know. This is a challenging integral. Now you can go in the Wolfram and see the answer. We'll show you how to do it in a couple weeks. It requires some pretty ingenious ideas that once you see them, you're like, oh, should have thought of that. Luckily, someone else did. So we can't, I'm telling you right now, you do not have to integrate it. If you look it up and do it, that's fine, but it's a long and tedious calculation, and it requires lots of knowledge we don't have yet. So instead of doing this, what I'd like to do is let's approximate it using a Riemann sum. So let's approximate with a Riemann sum. So what I'm going to say is I'm going to say that this integral, the integral from 0 to 1 of 1 plus 4x squared dx is approximately the sum. I said use 4 subintegrals. So let's say k equals 1 to 4. Take 4 terms of 1 plus 4x sub k quantity squared, and then this is our delta x. Right, so yeah, that's how you do it exactly, Zafalgar, but we will talk about that, as I said, in a week or so. So the point being, if you want to do this integral exactly, you have to introduce trig functions, and we'll talk about that soon enough. But right now, we want to think of sort of an ulterior way to get information. So let me remind you, you're going to have to take your mind back to Calc 1. What are these x sub k's? Well, remember, if we start with the interval 0 to 1, I want to break it into 4 pieces. So I know that means that this becomes 1/4, 1/2, 3/4. So my x sub 1 is 1/4. My x sub 2 is 1/2 or 2/4. My x sub 3 is 3/4. And my x sub 4 is 4/4 or 1. And don't forget your dx is 1/4. So for a few of you, you're going to have to go back and review how I'm getting these things. We talked about this in Calculus 1. We say you take your interval from A to B and you divide it up into n pieces. Here I want n to be 4. So the easiest way to visualize this is take a stick and chop it into 4 equal pieces. So here's a good way of doing it. I have my stick. I break it into 4 pieces. This is 1/4, 1/4, 1/4. Okay, now, you can do this with a calculator. You can do this with Desmos. I don't really care how you do it. I'll write it out this one time, and then, I'll show you how to do it in Desmos too. So if we write this out, this becomes 1 plus 4 times 1/4 squared, and then plus the square root of 1 plus 4 times 2/4 squared, plus the square root of 1 plus 4 times 3/4 squared. And then the last guy is 1 plus 4 times 4/4 squared. And now every one of these guys has a delta x, so I'm going to factor that out and put it at the end. Does anybody have a question about this? So my x sub 1 is 1/4. That's why I'm plugging 1/4 here. My x sub 2 is 2/4, so I plug it in here. The third term is 3/4. The fourth term is 4/4. Now, there is no reason in the year 2020 to do this by hand. So it's very easy. If you want, you can do this in Desmos. So let me show you how to do that. So let me go to Desmos. So is everybody seeing Desmos at home? Okay. All right, so look, here's how a quick way of doing it. Let's tell us what the function is. What was the function? Now be careful, the function we're trying to integrate is not x squared. We're trying to integrate that x, the square root thing. So we're trying to integrate the square root of 1 plus 4x squared. This is what we're trying to integrate. So I want to add this up. So I'm going to evaluate this at my 4 points. What are my 4 points? My 4 points are f evaluated at 1/4 plus f evaluated at 2/4 plus f evaluated at 3/4 plus f evaluated at 4/4. And then I have to put all these guys in parentheses, the whole sum, because every one of them has that delta x, which is 1/4. Whoa. And when I do that, you'll see that the calculator adds them all up for me. And I get 1.642. So let's go back to what I meant by this. So this is, here's the way you should think about this. This is f of 1/4. This is f of 2/4. This is f evaluated at 3/4. That's, you know, these are my x of 1s, my x of 2s, my x of 3s. And then this guy is f evaluated at 4/4, which is your x of 4. And then, of course, this is your delta x right here. And so when we have a calculator do that for us, we get 1.642. So this is approximately 1.4 or 1.642. Now, do we think this is a good approximation or a bad one? Well, we don't know. We'd have to do more sort of analysis. Maybe you say, okay, I trust Wolfram knows what it's doing. So maybe we go to the internet and then let's go to Wolfram. And let's ask Wolfram to integrate it. Wolfram is smart. So integrate square root of 1 plus 4x squared from 0 to 1. It's going to give us an exact answer, and we'll show you how to get that in a few weeks. It's going to be an ugly looking creature. But you'll notice that the exact answer is this scary thing, which most of you have never seen before. It's called the hyperbolic sine. But look at the answer. So a very good approximation is 1.47. So we're off by 2/10 almost. We got 1.6. That shouldn't surprise us, but what's that? Yeah, if we use a left Riemann sum, we would be under it a little bit. However, if you wanted a better approximation, you just have to use more terms. So we could integrate this from 0 to 1 using right Riemann sum n equals 4. That's what we use. We use the right Riemann sum. So it should know what this means. Yep, it does. 4, and look what they got. The same thing we did, 1.64277. Questions about this? Comments? By the way, it is very, we're going to talk a lot about what we're doing here. We're going to learn a lot other ways of integrating in the coming weeks. This method here, this approximation method, is very useful. It's called numerical integration. It's one of the more powerful tools used in modern science, computation, engineering. And we'll show you how to do much more effective sort of algorithms for this. If you go back to, you could see it, some of them. Wolfram, if you go to the bottom, they'll give you some more. See, there's some other methods they use. And you'll notice when you use these things like what's called Simpson's rule or Boyle's rule, you'll see that they're very accurate. So they're very close to the actual number. We'll show you how all this stuff works in a few weeks. It's pretty cool. All right, does anybody have any questions? All right, then look, you guys should be able to finish the homework. I'm not saying it's easy. If you have questions, you got to reach out, ask me, work together, the blind leading the blind. And I will see you guys Tuesday. Thank you very much. Have a good weekend. And unless I talk to you tomorrow morning. So hit me up if you have questions. Thank you guys very much. Take care. Someone has a question.